Thank you, folks. Good evening. So I'm now recording this session. I'm going to think about ratio and proportion. As always, I have the same objectives every day, every week, my same objectives to share these ideas. I don't know yet if any of you had an opportunity to try some of these ideas with your students. It'd be great. It'd be great if you did. It'd be even greater if you did and it worked well and you could share some feedback. You know, I tried some ideas on sequences, I tried some ideas on surds, and they went really well. So it'd be lovely to get some feedback from you if you try some things. But I do realise, of course, things are complicated at the moment, putting it mildly. Some of you may know from other things I do, I've been involved with the NCETM, the National Centre for Excellence in Teaching Mathematics, for a long time, for about 6 years. And early on in my time with the NCETM in September 2014 and indeed 15, I went to Shanghai. I had some visits to Shanghai. Thank you, taxpayers. I very much enjoyed my trips to Shanghai. And out of that grew the maths hubs. You may be aware of maths hubs. You may be aware of Teaching for Mastery, the maths hubs program, the CPD program run by the maths hubs. And when I think about Teaching for Mastery, I often think about this. This is a sort of a slide I made. This is my Shanghai takeaway. And I think this describes me, certainly described my teaching for a long time, thinking about activity. So I planned my lessons by thinking about what the children, possibly in different groups on different tables, were going to do in my lessons. And I realise, and being in Shanghai really helped me realise this, that wasn't the right approach. And the right approach was to think about, what do I want the children to think in the lesson? And so when I'm thinking about my objectives, when I'm trying to think, what do I think will intrigue, inspire you and enthuse your students? That's what I'm trying to do. I'm trying to think about what can you make them think as well as do. Do you remember we talked last week about factual knowledge, procedural fluency and conceptual understanding? So I do want the fluency. I do want to get them really, really good at doing the maths and doing the sums. I want them to have that procedural fluency, but at the same time be thinking, questioning, asking questions, reasoning, problem solving, etc. So thinking, you know, what's the light bulb that I want to turn on? What's the switch that I want to flick? And when I know what that is, then that suggests the activities. And that's kind of what's been behind my choice for today. So sort of two sections, but quite you know, each section quite chunky, quite meaty, or quite tofu-y if you're practicing veganuary. So we're going to think about combining ratios, and we're going to think about representing proportionality. I haven't got any of the what you might call standard ratio questions. So things like sort of you know, if A to B is 3 to 7 and B to 7 is 5 to 4, what's A to C? I've not included any questions like that because I think that is pretty straightforward, and you know, students know pretty much what to do. I have got some questions about ratio sharing. So that sort of idea of, you know, A to B divide some money in the ratio 3 to 7, because I think you can enrich that. You can make that more conceptually demanding, and I'll show you about that when we come to it. So let's just jump in with combining ratios. So every time I pause, by the way, it's because I've just suddenly noticed somebody else then entered the waiting room. So I have to quickly let them in, and I can't multitask. If you saw the front of my car and the massive dent in it, you'd realise I'm not very good at doing two things at once, like turning and looking in a mirror. Anyway, so here's a question, and I do lots of questions like this. I'm just quite interested to have a look at it. We are, by the way, going to come back to variations on this question. The next sort of 5 slides or so are all variations on this question. So sort of perhaps just sort of notice the key features of it. You've got red to green, you've got something about sweet and sharp for red, you've got something about sweet and sharp for green, and we're asking about the overall. So essentially we've got a group with properties of red and green, and then within the group there are the subgroups, the red and the green, and the subgroups have sub-properties, and we're trying to combine the subgroups and the sub-properties back into the whole group with the whole property. That's kind of the idea with these sorts of questions. And we're going to do some quite subtle variations on them, which I hope will give you some ideas for that challenge, that richness that we're looking for when we're teaching the highest attainers, but which is also worthwhile. It's not just challenge for the sake of it. It is actually inherently worthwhile. Slightly, I'm talking to give you a chance to sort of digest the question, pun fully intended, probably being about apples. Any thoughts about how your students might go about solving it? Not so much how you would solve it, because I'm sure you've got lots of good ideas. What do you think your students would do? What might they do first? Throw up their hands in horror? I don't know. I'm interested. What responses do you think your higher attainers might suggest to a question like this? pop some thoughts in the chat if you've got some. So thinking about fractions, lowest common denominators. Yeah, so definitely converting to fractions, convert ratios to fractions. So I think they would. I would almost put money on the fact that you will see some 3/5 occurring and some 1/3 occurring. I'm absolutely sure that because they will have learnt something about exactly, Anita, that misconception. And then Claire, exactly, yes, I'm not for one moment claiming this is an original question. I mean, literally, this is an original question, but the idea of fractions very much is a very common GCSE question. Much like some bars. Just coming back to this point about fractions and ratios, you will see that. You will see some 3/5. Apologies. Of course, if you see your 3/5, you might then ask them, well, what's the other fraction? 5/3. You know, so that you might start seeing some 5/3. Are you really going to see some 3/2s here? So hopefully they might realise that these fractions don't quite make sense if they start drawing fractions. I absolutely agree about a pictorial representation. So thank you, Priyesh, for suggesting that. You can do these bar models. It's not what springs to my mind. Yeah, exactly. Well, that now, so Yuvraj, that's a really interesting question about the relationships. Yuvraj put in the chat about 3/5 of the ratio value. I think it'd be really interesting. I'm going to come back to fractions and ratios a bit later, Yuvraj. So hold that thought, hold that question, but we'll come back to it. Yeah, so you're right, Xavier. They would kind of add up. They go 8, 5, 4, and then not know what to do with it because it's not a sharing question. This isn't, well, okay, it is a sharing question, but we haven't got an amount to share explicitly. So I think it's really interesting to kind of get their auto responses and try and get them to realize why their auto responses are not actually going to be very helpful. That's what I was thinking, Roger, a tree diagram. Yeah. So that's what I would want them to suggest is a tree diagram. This is how I think of this question. So it's a tree diagram, and so I think of red and green. So then the fraction of red is 3/8. I'm really emphasizing why it's 3/8. And then the fraction of green is 5/8. And then we've got sweet and sour. So let's have nice face, nasty face, or happy face, sad face, sweet and sour. And then obviously for red, it's 3/5, and therefore sharp must be 2/5. And then green is 1/4, and sharp is 3/4. And then from there, obviously, we can then work out the total amount. And this comes in with, Claire, what you were saying earlier about fractions of fractions. So for red, it's going to be 9/40, and for green, it's going to be 5/32. And then we can add those two together. And I have got my common denominator of 160. So it's going to be 36 and 25. So it's 61 out of 160. And so the answer, make sure they actually finish the question. Amazing how often they don't finish the question. 61 to 99, which won't simplify, no, because 61 is prime. So I would think of this as a tree diagram question. And actually, I would do something like this before any work on tree diagrams in the probability context. It's partly why I've done this today. So I would do these with my class before I did anything on probabilities and tree diagrams, because it seems to me much more obvious that what you do with tree diagrams, you multiply along the branches, you add the different branches, makes absolute sense with concrete objects like apples. Obviously not literally concrete, but you know what I mean, real world objects like apples, much more so than it does in the context of probability. So you can, if you want to, if you need to, you can actually say, look, I've actually got some apples. I can even draw a tree. I've actually got some apples, and actually 3/8 of them are red, and actually 5/8 of them are green, kind of, etc., etc. And they can really imagine I'm taking literally 3/5 of the red apples, and the red apples are 3/8 of the orchard, and they can really see why it's 3/5 multiplied by 3/8 plus 1/4 multiplied by 5/8. Whereas I think when you try to do that, at least I find when I try to do it in a probability context, it's much vaguer why that's the case, why that works. So these are all tree diagram questions, and that is good practice, is good arithmetic there. I deliberately chose those numbers so they had quite a nice common denominator, but not a trivial common denominator. Then I might tweak it to make that question. So I'll draw the tree diagram. Can you see the 3 to 5 is the same, the 3 to 2 is the same, but now it's overall it's 1 to 3. So now I've given you the answer, the end point, and the question is, what's it for the green apples? So we've got red to green, we've got the same thing, we've got 3/8 and we've got the 5/8. And then we've got, I'll always do sweet at the top and sour coming down. So we've got sour pointing to the second down. So 3/5 and 2/5. And then we don't know for the green apples, but we do know that overall, the ratio is 1 to 3, so the fraction is 1/4. Okay, obviously being careful again about the fact the ratio 1 to 3 is equivalent to, well, and we'll come back, particularly you, the point you raised. We'll come back to the relationship between fractions and ratios shortly, but one thing of the answer is being 1/4. So what are we going to do here? Now, hopefully your higher attainers will know algebra, will think algebra. We want to algebraize this problem. We want an X somewhere. So they may well sort of think, well, this is like, this is sort of X to Y, or sort of something like, they may of course think X to X. So they might think X to Y, but then that makes that really complicated, because then that has to be X over X plus Y, and that has to be Y over X plus Y. So get them to think about not only that they want to algebraize it, but also how to algebraize it. What's the best way to algebraize it? And that's not the best way of doing it, because that's got 2 unknowns, got 2 letters in it. And we don't really need that. So get him to realize that actually all we just need is an F, is a fraction here. We can work out the ratio later once we know what the fraction is. So get him to realize that we can do it with 1 letter, F, not 2 letters, X and Y, or P for proportion maybe. In which case then what's this? Well, hopefully they'll see it's 1 take away F. It doesn't actually matter here, it doesn't matter on the next question. So what do we get? We're going to get that 9/40 plus 5/8 of F equals 1/4. And so 5F over 8 is 1/4 taken away 9/40, which is 1/40, because we're taking 10/40. And so we get that F is, so that's 8 down there, 1/25, I think. Okay, and then from that we can work out that the ratio must be 1 to 24. Okay, so that looks like an S, like a scale fact, doesn't it? No, it should be a 5. Okay, so algebraize, but how do you algebraize efficiently, successfully? Okay, so now what have we got here? So now we've got the same tree diagram. We've got the same tree diagram, but, well, as you can see from the question, what you haven't got is the red to green ratio. We haven't got the red to green ratio. We've got everything else, but we haven't got the red to green ratio. So if we go back to our usual picture, so we have got 3/5, 2/5 for sweet and sharp. We've gone back to our 1 to 3, so we've got 1/4. Sorry, I should do that in green, really, shouldn't I? So we've got our 1/4, 3/4 for the green, sweet and sharp. But what we haven't got is the beginning, is the first branch of the tree diagram. So now hopefully we're a bit more comfortable to call it F and 1 take away F. And then what do we know? We know the overall ratio sweet sharp is 5 to 7. And so what we're thinking about is a fraction, say, of 5/12. Sweet has got the fraction of 5/12. And so we know that 3/5 of F and 1/4 of 1 subtract F has to equal 5/12, etc. from there. So that's, we can then go on and solve that. So you can see we've gone from no algebra to 1 occurrence of algebra, if you like, to 1 variable, but now occurring twice. So I hope you can see the progression in these questions. Okay, so now what have we got? So okay, so we've gone back to the ratio 3 to 5. Okay, so we've gone back to the ratio 3 to 5. 3/8, 5/8, and we've got red apples, the ratio sweet sharp is 3 to 2. So we've got 3/5 and 2/5 for the red apples. And green, we've gone back to 1 to 3, so that's okay. So we've got 1/4, 3/4. I'll make that a bit more legible, sorry. 3/5, 2/5. And now we're asked, what fraction of the sweet apples are red? Now, what I think the students will say is, well, isn't it 3/5? Isn't the answer 3/5? So get him to articulate that 3/5 is the fraction of the red apples that are sweet, and we're asked the other way round, what fraction of the sweet apples are red? I think that's hard. It's hard to do verbally, and it's particularly hard to do if the first time you come to it. What you might be thinking of, what we might be thinking of with our wider mathematical knowledge is this. Basically, this is a conditional question. So essentially what you've got here, if you like, in probability terms, what you've got here is 3/5 is the probability that an apple is sweet given that it's red. And what we're being asked for is the probability that it's red given that it's sweet. And get them to think about, well, the 3/5 means that if I take a big barrel of red apples, 3/5 of them will be sweet. But I'm now being asked about a barrel of sweet apples, some of which are red and some of which are green. And the question is what fraction of that barrel of sweet apples is going to be red? And trying to get them to realize sort of physically what the difference is, in the real world, what the difference is between these two contexts before they try to answer it. And again, I'm doing this partly to set up some ideas around conditional probability, which I suggest doing informally with high attainers. And we'll look at that in a future session. So how do we do it? Well, let's work out what have we got here. Well, we know, don't we, that that's 9/40ths, and we know that's 1/32, and that we know that when we put them together, that's 61/160ths. So that is my sorry, that's supposed to be an arrow, not it looks like an inequality sign. An arrow. So we know that if you like, is my barrel of apples. That's my barrel of sweet apples. And I want to know what fraction are the red ones of that. So I want 9/40ths out of 61/160ths, which obviously is going to be 36/61. I suppose we could sort of say what's the ratio of, amongst the sweet apples, what's the ratio of red to green? So we've got some linguistic sophistication there, and also some conception sophistication. The fact that we flipped it round from knowing about the apples, knowing that the apples are red and asking what fraction are sweet, to knowing that the apples are sweet, crunch, oh, lovely sweet apple, open your eyes, is it a red one? We can sort of think about physically how you might do this. And then finally, I would perhaps do a question like this, where you can just see basically from the decreasing numbers, you can see how there's less and less information in each of the questions. So we've still got our 3/8, 5/8, and then 1/3 of the sweet apples are red. Okay, so that's right at the very end. Okay, and then we don't know anything about the red apples, or indeed anything about the green apples. So now we have got the situation where we have two variables. So we've got x there being, say, the fraction of red apples that are sweet, and y being the fraction of green apples that are sweet. Not x and x for obvious reasons, but again, your students might suggest that. So what have we got here? We have got that all the sweet apples sort of add up to 3/8. Also, the fraction of apples that are sweet is 3/8 x plus 5/8 y. And of that, the red ones are 3/8 of x, and that has to equal 1/3. So that's the equation we're solving. 3/8 of x out of 3/8 plus 5/8 of y must equal 1/3. Now, of course, they can't solve that. That's not going to give them x equals and y equals. There's only one equation, two variables, and hence this interesting question about which one turns out to be larger. And of course, they might be wondering, well, if I don't know the values, how am I going to work that out? And so tracking it through and realizing they can make an inequality statement, they can make a comparative statement without knowing the values of either of them, is just really good productive struggle. It's really good conceptual challenge as they track it through. So, I want them to be good at ratios. I want them to understand how to convert between ratios and fractions, as we talked about at the beginning. I want them to know, I think was it Xavier, you said that you don't always just add up the fraction, add up the parts, and then try and do some division. Not all ratio questions are the same. So that's why I think these are good questions, because they really confront a lot of those misconceptions. And you can see the progression, and when you get the slides, you're better going to work this through yourself. You can see the progression of how I'm either taking away information or I'm moving around the unknown, and I think making it more complicated, making it richer as they do so. but I wouldn't kind of go through. I wouldn't do what I've done with you. Ironically, I wouldn't go through one example of each type. I just say, work it out. You tell me what you're going to do. What do you know? What do you not know? What do we do with stuff that we don't know? We call it a letter. We call it an X. We call it an F for fraction. And you tell me what's going on. They don't need worked examples all the time. They can work this out in groups or by themselves. I shared this slide with you before, but I felt it really applied to that set of questions. What's the same, what's different? What have I changed? What haven't I changed? What's the same, what's different? I suppose, and why? What's the effect of that? What does that matter? And then, of course, make it your own. Once they've got the hang of this, they can so get on with making up their own questions, answer each other's questions. Can they make them a hard question? Can they make them an easy question, etc. And then I just thought of a different context for it. So this is a very similar sort of thing. Put a bit of percentages in. So kind of clearly we're going to have the 0.7 for the muesli and the 0.7 for the morning magic and 0.3 for the breakfast boost. And then we're going to have the same thing. We're going to have oats being 3/4, nuts being 1/4, oats being 8/9, nuts being 1/9, etc. So we can work out oats to nuts from there. And that's relatively straightforward. And then that's the other way around. So this is a similar sort of problem, as in now we don't know the proportion of morning magic or breakfast boost, but we do know the final answer. So we've got the 3/4 and the 1/4 and the 8/9 and the 1/9. And so now we're saying we want 3/4 of P plus 8/9 of 1 subtract P to equal 5/6. And so I'm obviously go about solving that equation. And then I thought this generalizes into this idea of what can you get? So if we go back to that answer, if we take not the entirety of that answer, if we take that answer, so that is the that is that the oats? Yes. So that's the proportion of oats. And if we take that, so we've got 3/4 of P plus 8/9 of 1 subtract P, and we want to think of that in proportion to the nuts. So it's 1/4 of P plus 1/9 of 1 subtract P. What's possible? Well, obviously simplifying it a bit. So if I expand the brackets, I'm going to get 8/9 and then 3/4 take away 8/9. Oh, bit of mental arithmetic for me on a Wednesday evening. So I'm going to get 27/36 take away 32, 26, 36. So I'm going to take away 5/36. Is that right? Yeah. 2, and then I'm going to have 1/9 here, and then going to be 1/4 take away 1/9, so it's going to be 5. It's going to be plus 5/36. So what's possible there? How do I get 5 to 1? A good sense check, by the way, to get them to realise, draw out a sense check. Well, what happens in the limiting cases? What happens if P is 0? What happens if P is 1? What happens if I have no morning magic? Well, I get 8/9 to 1/9, which is 8 to 1. Well, that makes sense because it's pure boost. And what happens if I have no boost? Well, then I get 8/9 take away 5/36. So that's going to be 32/36 take away 5/36. So I'm going to get 27/36. And there's going to be 1/9 plus 5/36, which obviously is 9/36, which is 3 to 1, which is what you want, because if you have all magic and no boost, you must get the answer 3 to 1. So it's quite good to get them to realise that there's a sense check here. That they can check that formula, those calculations are correct. Those not calculations, those simplifications are correct by thinking about what happens in the extreme cases, and that's just a good habit to acquire. And then thinking, well, it's got to be between 3 to 1 and 8 to 1. Can it be 4 to 1? Can it be 5 to 1? Can it be 6 to 1? Can it be 7 to 1? Can it be anything in between? How am I sure, etc. And then a nice little sort of sophistication on this is to move to not equal quantities. So with tins of paint, where the tins come in different sizes, so if they have sort of X tins of Pacific and Y tins of Sapphire, X tins of Pacific and Y tins of Sapphire, then really what they've got is they've got 2X litres and 5Y litres, and then that's what's being split in the ratio of 1 to 7. So with 1/8 being white, 7/8 being blue, 1/4 being white, and 3/4 being blue. And so they're not working with fractions of X and Y, they're working with fractions of 2X and 5Y. And how does that change things? You know, what complexities does that add? Does that make some answers impossible, say, for example? I like this. I absolutely won't claim any credit for this. There's a really nice enrich activity about mixing paint. If you just look on enrich for mixing paint, you'll find it pretty straightforwardly. What I like about it is that there's a sort of there's a slider. There's a graphic. So as you move a slider up and down, the color of the paint changes. It's red and white paint, so it becomes either more and more red or more and more white. You know, with some agenda shades of pink in between. So it's just it's a really nice way of doing this. And obviously with online learning, you might as well take the advantage. You could actually ask them to go and do that. You could set them to go and play around with Enrich as part of the lesson, and then get to come back and experiment with and share what they'd investigated. So that's what I would do with tree diagrams and combining ratios. For the reasons I've said, I think it develops their fluency, develops their understanding of what's meant by ratio, and it makes us think about what's the relationship between ratios and fractions. So you're absolutely right. I do want them to be saying, well, look, X to Y is 3/5 means that X over Y is 3/5. I want them to have that procedural fluency because that's really useful. But what I also need them to have some understanding of where on earth that comes from. Because if ratios are like fractions, if it's just, well, look, you know, if what they're thinking is you just do that, you just turn a colon into the vinculum, into the fraction line, then what on earth do they do there? It can't be true that ratios are just like fractions, because what do you do in that case? I mean, you know, what does that mean? What does a triple decker fraction mean if it means anything at all? So it can't be true that ratios are just like fractions. There has to be some understanding to get to that point. Lots of ways of getting there. I would, and this picking up something somebody said earlier, I'd draw a bar model. I'd think about this being a bar model. So I would say how I would interpret this is saying is I've got 3 equal parts and 5 equal parts. So that's X and that's Y. I can think of X as being made up out of 3 equal parts and Y being made up out of 5 equal parts. But that tells me that those 2 parts are equal. But what are those 2 parts? Well, one part is X over 3, that's that part. And that part is Y over 5. And therefore, those are equal. X over 3 equals Y over 5. Now I can do the mathematics. So now I can multiply both sides by 15 by the lowest common multiple. And then that tells me that 5x equals 3y, and then that tells me that x over y is 3 over 5. And that's my conceptual understanding. So yes, it is true that x over y equals 3 over 5. That's a really useful fact. That's really useful bit of fluency to have to hand. But where does it come from? I would bring it from the tree diagram. Sorry, not tree diagram, from the bar model. I get it from the bar model and make sure they can give me that argument. Because then you see, when we come to this, I can have my x, my y, and my z. I can have my 3 equal parts. That really does not look like equal parts. Let's just draw that again. So I can have my 3 equal parts. I can have my 5 equal parts. And I can have my 2 equal parts. And then I've got that x over 3 equals y over 5. Sorry, I'm pushing the z there. Didn't mean to do that. Equal y over 5 equals z over 2. And then I can do something from there. For example, what I could do is I could multiply through by 30. I could multiply each term by 30 because that's the lowest common multiple. And so that I would get that 10x has to equal 6y has to equal 15z. So there is a relationship involving x and y and z. But it's not as straightforward as in the 2 case. So I absolutely agree. I think you've read. I think you who said it. They absolutely kind of think they're the same thing, and they are telling them similar information. But I don't think they should just be automatically thinking, well, one of them translates without thinking to the other, because it doesn't work when you have more than 2 parts. So having kind of made sure they were happy with that, then I might do a question like this, yeah, they'll draw a picture, and then it'll be really interesting to see what they do. So, you know, they might sort of say that's sort of 3x and 5x. They might sort of say it's kind of 3x and 5y. They might say it's 3 and 5. I think it'd be really interesting to see how would they take, say, that automatic response and put it onto the diagram. You know, so what they might want to, they might sort of call that x and y, and then go, well, what does that mean? Well, I could rearrange that and then say sort of, oh, does that mean x is 3y over 5? And those people will get one answer, and people who said, well, look, why can't we just sort of say it's 3l and 5l, because they're in the ratio 3 to 5. And then they would get an answer, and would they get the same answer, and why do their answers look different in the middle? So I think that's a really good activity to get people to compare their different solutions, and, you know, what's different and why, and does it matter? And then something like this is where that fluency is really handy, because you want them to be able to go, oh, okay, so the sum is x plus y over x, and the difference is x subtract y, and so I want that to equal 5 over 2, and so I get 2x plus 2y is 5x subtract 5y, and so I get 7y is 3x. And then sometimes they get stuck. You might sort of see something like x to y is 3 to 7. They might sort of flip it around, say 3x 7y, so 3 to 7. So I often find they're not actually great at doing the backwards argument. So x over y is equal to 7 over 3. And so the ratio is 7 to 3, not 3 to 7. They tend to fixate on the coefficients and go, well, look, x, y, 3, 7. So the answer is 3 to 7. No, it's 7 to 3. It's the other way around. And then, of course, you can do something with the 3 case. So similarly, what does the picture look like? So it's 3 to 5 to 2. So, and does it matter which way you draw it? I mean, I've sort of drawn this. What was I trying to draw here? A rather generous 2, 3, 5. But, you know, do I have to write them as like we did here? Do I write one of them as fractions of the other? Can I just write them all as 2, you know, 3k, 5k, 2k? If I approach it differently, do I get the same answer, etc.? And then, of course, the same thing, but with sums and differences. So thinking here about, you've got 3 facts. We've got x plus y over x subtract y is 7 over 1. We've got z plus y over z subtract y is 11 over 1. And we've got x plus z and x subtract z is 19 over 1. So I can get x in terms of y, z in terms of y, x in terms of z, and then what do I do with that? And how do I put it all back together? So that's the struggle. So certainly, again, I was saying earlier, I'm not going to go through a worked example with this. I'm going to say, well, look, you know, if you can do it in the 2 case, you can work out how to do it in the 3 case. There's that great phrase, I think it's by Gattegno, Caleb Gattegno, the educationalist Gattegno. He says, teach the little that leads to a lot. And that's just a really nice phrase, teach the little that leads to a lot. And you get the right idea of turning ratios into fractions, or expressing the information equivalently, then a lot of questions come out from it. So changing ratios then. So here we've got, you know, it's kind of a classic question about sharing some money, a little bit of a complexity to it. So they share some money in the ratio 7 to 3, and then A gives B £10, and now it's 3 to 2. So actually they share it in the ratio 7 to 3, but then A gives B 10. So A loses 10, B goes up by 10, and now the ratio is 3 to 2. So I can think of that I can express that equivalently as a fraction. So I've got 2A take away 20 equals 3B plus 30. So I've got 2A subtract 3B is equal to 50. But what else do I know? I also know that at the very beginning, that A over B equals 7 over 3. And so I get 3A is equal to 7B. And so I can solve those simultaneously, dot, dot, dot. And assuming I've done my arithmetic correctly, you should end up indeed actually with A is 70 and B is 30. Because that is in the ratio 7 to 3, and then if you give away £10, that will go to 60, and that will go to 40, and that obviously is the ratio 3 to 2. So relatively straightforward sharing problem. Right, so now we don't know the amount of money. There's a whole number of pounds, and we know they each get a whole number of pounds. So we're working with integer multiples of pounds, or actually natural number, positive integer multiples of pounds. So now we've got A subtract 10 over B plus 10 equals 3 over 2. Well, that's the same, so it's going to simplify in the same way to 2A plus, sorry, take away 3B is 50. But that's all I know. There's no other information, except there's information about getting a whole number of pounds. So A and B are integers. Okay, oh, sorry, Roger. Do we need two variables? No, we don't actually. No, that's really nice, actually. Nice suggestion, Roger. At the beginning, just go straight away to, yeah, so, I mean, I guess the only complexity is you'd end up with them with fractional, one of those have a fractional coefficient. So, oh, I see. You say that A is 3x and B is 7x, or possibly the other way around. Actually, it's going to be 7 to 3. Okay, yeah. So they write them in terms of the third variable. Yeah, nice. That'd be nice. That no. So we don't need to. I guess we need to because I'm thinking ahead to this one here. I was thinking about the A and the B because I knew where I was going. But I agree for that question, you could do it with just one. And then interesting discussion here is why can't you do it with just one for that question? Yeah, exactly. Yeah, so that would work nicely. Whereas here we do need to, because I haven't given you the other bit of information. So we need to step up the algebratization. But thanks, Roger. Thanks for that suggestion. So now what do we know? Got a whole number of pounds. So what are the possibilities? Well, obviously A could be 25 and B could be 0, if that counts. And then A could be 26. No, that's not going to work. I'll make it 52. A could be 27. That'd be 54. No, that's not going to work. But it could be 28 because that then would be 56, obviously 56. And then I could take away 3 lots of 2. And then it could be, next one is 31 because that would make 62. And then obviously I'd take away 3 lots of 4, etc. Now, what are we noticing? This looks like this is going up in 3s. And this looks like this is going up in 2s. That's interesting. Is that true? Is that a coincidence? Well, if I go further on in this sequence, will that pair always satisfy this original equation? Well, of course, that they can start thinking about what's an expression for the value of the nth term of each of these sequences. So hopefully they'll say that this is 22 plus 3n. And this is -2 plus 2n, and then they could see if I substitute that for A and that for B, will those expressions always, sometimes, or never satisfy the original equation? And the answer is you can see by doing the algebra that they will. That basically the n terms will cancel, and we'll end up with 44 plus 6, which equals 50. So they're quite nice. They can start to explore which values are possible and then recognize, at least for some of the values they've written down, there's a structure to those values, and then use that structure to verify that this is always the case. And again, this might be ringing a bell for you. What we're really thinking about here, what are called Diophantine equations. So Diophantine equations are equations which have integer solutions. So we're looking for a Diophantine solution to that problem. And then, of course, what I've done now is I'm now taking out even more of the structure. I've just gone for some of it. So I've got A subtract now K, and B plus K has to equal 3 over 2. And so I've got 2A take away 3B is equal to 5K. So we've looked at that for K equals 10. What about if K is not 10? Is that sometimes soluble? Is that always soluble? Is that never soluble? If you choose any whole number of K, will that always have a solution? And if it does always have a solution, does it always look like this? I.e., I can build up a general formula using my knowledge about linear sequences. Will the solutions always be a linear sequence? And you can just think of all the exploring that could be done with that. And actually, I haven't prepared the slide, but probably I should have done, is of course the other thing we can do is we can change the 3 to 2. So what happens if I have, say, 3 to 5 there, or what happens if I have, obviously I had 4 to 2, I can cancel it down. What happens if I had, say, sort of 1 to 3 there? Am I always going to be able to solve the resulting equation? So again, teach the little that leads to a lot. Give them an idea, and let's see where they go with it. A couple more questions. I dug this one out. It's probably not very appropriate. I realise now 45 gallons of wine. You might want to change it slightly, but anyway, that sort of thing. And then questions like this, I think are really interesting to see how the students engage with these sorts of questions, because essentially there's 2 bits of information going on here. So we've got speeds, so we've got, or velocity if you like. So I've got red velocity to blue velocity is 3/2. And I've got red time over blue time is 5/6. And I want to think about the distances. So I want red distance over blue distance. And then think about how do they combine. Now, obviously, what this is hopefully prompting in there for them is maybe something like that. I try to remember to use velocity, and I try to remember putting it in the right place as well. So velocity, distance, time. I think about, oh, okay. So what we need then is we need to have red velocity, red time multiplied by blue velocity, blue time. And how do we extract that from the 2 previous fractions? Well, looks like we multiply them together in this case. So now procedurally it's quite straightforward, but conceptually getting to that point I think is a good struggle. And that leads us into the second section, which is thinking about representing proportionality. So something like this: you've got a train traveling at constant speed. Now we're going to reduce the speed by 20%. How does the duration change? Well, so we could use a calculation. So we could say, well, look, the duration is the distance divided by the velocity. So presumably the return journey, presumably the distance is the same. So it's now distance divided by, well, it's 0.8 of the velocity because it's been reduced by 20%. What's that? So essentially it's 1 over 0.8 lots of distance over velocity. So what's that? Well, that's 1 over 4/5, so that's 5/4 of the original, and so it's 1.25 of the original. And so what happens is the time goes up by 25%. The time has a 25% increase. So a 20% reduction in the speed gives us a 25% increase in the time taken. That's fine. It's a piece of numerical work. It'd be really nice, I think, to try and show it. So if you're thinking about distance being velocity times time, what you're thinking about is a rectangle, and the distance is the area of the rectangle. So if it's got width v and length t, then distance is area. And that's a very powerful way of thinking about the distance in a velocity time problem, or thinking about the mass in a density volume problem, because obviously mass is density times volume, or thinking about the force in a pressure area problem, or ultimately, of course, thinking about the constant of proportionality in inverse proportion. Because if you've got x is k over y, then you've got k is xy, so k is the area of the xy rectangle. So what's happening here is that the velocity is being reduced by 20%. So if you like, I could cut it into 5 strips. And then what I want to do is I want to remove that strip. I basically want to get rid of that strip, but I don't want to get rid of it because the distance is the same. So I don't want to remove it, I want to move it. I want to move that strip, that area, up to here, so that the area stays the same. So D stays the same, the area stays the same, but the dimensions change. So the question is, how much more length do I need with this reduced width so the area doesn't change? And we can see that by, if we chop up into 4 parts, because what we've got is that if I call that A, B, C, and D, then that's A, that's B, that's C, and that's also D. So I can imagine move, because all these parts are the same. So sorry, all these parts are the same area. I've cut it into 20 congruent pieces, 20 equal parts. And so actually what I want to do is just slide them along there. And therefore the extra strip, which is as wide as a quarter, i.e. there's your plus 25%. So you've got 1, 2, 3, 4, 5 quarters. There's your extra 25%. And that area is the same as the area of the longer but thinner strip that you ripped off the bottom. And we can see that by cutting it up into 4 pieces and rearranging those 4 pieces. I think that's just a really powerful pictorial argument to explain what is going on here with the calculations. And then you've got something sort of here, something sort of similar. Now what have we got? So we've got, again, a train traveling. So we've got a V and a T, which gives us a D. Now what happens? So the D gets 20% bigger, so 1.2. And the V gets 50% bigger, so 1.5. So I have got sort of length scale factor, area scale factor questions. But of course, these are not similar. These are not similar shapes. These are not similar shapes. So therefore, it's not the case, obviously, that 1.5 squared is 1.2. You know, we know that's not the case. And therefore, what is the missing T? So what is the scale factor there? And how would they work it out? So just thinking about those visual representations. Oh, thank you, Priyesh. Thank you, Roger. I'm glad you like this. Where I find it really helpful, by the way, quick sideline. Where I find it really helpful is with those problems where you've got some journeys happening 2 ways, and you've got 2 different distances, and you put them together to find the average. Because what you're saying is that I've got a distance here and a distance here. So I've got one rectangle, another rectangle, and I put them together to make a total rectangle, total area. And I want to know what's the area, what are the dimensions of the overall rectangle. So I mentioned proportionality a moment ago. This is your classic. So 4 cows take 9 days to graze a field. So, you know, if you do it by fluency, you just go, well, cow is inversely proportional to the number of days, or perhaps the other way around, actually. Perhaps the cow, the number of days, inversely proportional to the number of cows. And so cow times day is constant, put the numbers in. So I got cow times day is 36. What does that mean? That means you've got a rectangle. You've got a rectangle, dimension cow and day, and area 36. Well, 36 what? 36 cow days is the amount of work. So this is the amount of work that has to be done. And it's 36 cow days worth of work needs doing. So that means if I have 4 cows working for 9 days, or chewing for 9 days, they will do that 36 cow days worth of work. But if I only have 6 cows to do the 36 cow days worth of work, it must be 6 days as well, which of course is the same as doing 36 divided by 6, but it's just explaining what is going on. Actually, I've not drawn that really well because of course the whole, well, I'm sorry, I want to make it look a little bit wider than I did, okay? So you've still got the 36, the total amount of work hasn't changed, but it's changed shape from being a rectangle to, in this case, being a square. And I think this becomes really helpful with questions like this. So I've got, now what I've got is I've got my 4 cows and my 9 days, and in their 36 days, they can graze 1,000 square meters. In their 36 cow days worth of work, they can do 1,000, they can graze 1,000 square meters. So if actually they've got 2,500 square meters, we've got another 1,000, another 500. What that means is another 36 cow days, another 36 cow days, and then another 18 cow days. So altogether, the total amount of work is 72 plus 18, which is 90 cow days worth of work. So you've got, so 1,000 meters is what 4 cows can do in 9 days. So that's 36 days worth of work for cows. And then another 1,000 and another 500 adds up to 90 cow days worth of work. So if I've only got 6 cows, then that's going to take them 15 days to do it. It'll take them 15 days to do it. Now, of course, you can do this numerically, and the standard argument would be sort of something like, well, it's 9 days, and then the extra area increases the time, is an increasing scale factor, because there's more to chew, whereas the increasing cows decreases the scale factor, is a decreasing scale factor, because more cows means it'll take less time, there are more mouths. So you can do it like that. And then obviously do a bit of simplifying, and we are going to get that, that's 5/3, and then that's going to be a 3, and then 3 and 4 is 12. I'm suddenly panicking because I seem to have the answer. Why have I not got the answer 15? What have I done? Let's try that again. All going so well. Sorry, folks. Right. So it did take them 9 days. It was 9 days, and then I've got more area. Oh, sorry, it's over 1,000. Sorry. Thank you, folks. Thank you. It's over 1,000, not 1,500. I don't know where I got 1,500 from. Sorry, it's over 1,000. Thank you, Priyesh in particular. Thank you. Phew. Right. So back to where we were. So that's now 5/2, and so I get 2, 6 is 12, and so therefore that gives me a 3, and then the 9 and the 3 gives me another 3. So altogether I get the 15. So you can definitely do that, and that's quite a good argument. Is the area an enlargement? Yes. Is the increase in cows an enlargement? No, it's enlargement with the fractional scale factor. It's a shrinking, it's reducing the amount of time. But I just think the picture works really well. So then my question to you is, what happens in that case? What happens here, where you've now got more variables? So procedurally, you would say, right, what have we got? So we've got how many biscuits? So it's a question about biscuits. So it's 60 biscuits, right? There are fewer decorators, 7 and 5, so they're going to eat fewer biscuits, but they're here for longer, so they're going to eat more biscuits, and they're working on a bigger wall, so they're going to get more hungry, and so that's the calculation. So that's the calculation, and therefore I'm exactly, Roger. Do you have to draw a cuboid for it? And can my drawing manage it? No, it can't. It's a straightforward answer. Okay, and then finish it off something like that. You know, so I'm thinking here, what's happening here? So now you see we haven't got any calculations. So what would this look like? So we've got you know, I've got my rectangle. Well, again, let's do it procedurally. So here's the time. Now, if there are fewer trees, they're going to take less time to eat it. And if there are more giraffes, they're going to take less time as well. So it's an inverse scale factor for the giraffes. Sorry, it's 20% more giraffes. Sorry, so that should be a 1.2. That should be a 1.2. And right, let's just start that again, because it's 40% fewer trees, so it's 0.6. Sorry, I thought it was 40% of the trees. No, sorry, it's 40% fewer trees. So it's 0.6 is the scale factor of the trees, and it's 1 over 1.2 because more giraffes means it'll take less time. So that's it procedurally. What does it look like pictorially? What's the rectangle? How is the rectangle changing? And again, I would say, you know, for each of these questions, you could say, give me a calculation, give me a picture. So give me another example, give me another method, give me another diagram, give me another reason. And then, of course, they can make up their own exactly as you would like them to. Thank you very much. I will pause there. I will shortly send you a clean deck of the slides to experiment with. I will also send you a link to the evaluation. Thank you, those of you who evaluated so far. It'd be good to get a few more evaluations, please. It's not me being vain. I want improvement points as well as praise. It's not me just being self-centered. The people who pay for this like to see some evaluation. They like to know that what you are getting is of some use to you, and they also like to see how I respond to the feedback. They're keen to see how I take on board the feedback that you give. So it's really useful to get some comments. Take about 5 minutes. I will send you a link to for this one and for the previous ones, if you've not had a chance to do so, I would really value it. But I know you are phenomenally busy at the moment, and juggling all this is complicated. I absolutely recognise that. So I will pause there. I will stop recording. Thank you very much.